And if we see that the variance, or maybe not variance, because variance means a certain thing, so maybe the change in the data between here and here, we're trying to see statistically whether it's a significant enough difference to indicate that there is something else going on here, and not just like some by chance that these all happen to be larger numbers than the other ones. So that's what we're looking at. Okay, last two problems. I'll be less talky, I promise. The two IB schools would like to compare test results of their students. They randomly picked 10% of their second year students and checked their test results on a test where the maximum mark was 60. The table below shows the results. Assume that the tests followed a normal distribution and the variance is the same in the two schools. So null hypothesis, go ahead and tell me what the null hypothesis is. Remember that our null hypothesis with a t-test will always be that the averages stayed the same. So mu1 equals mu2. Okay. And we're assuming that this is going to be our mu1 and our mu2. We know we mean averages, but this is going to be the average for school A, and this is going to be the average for school B. So for your alternative hypothesis, I want you to go ahead and take your best guess or your best attack of what you think the alternative hypothesis is. So skimming through here, in the wording of the problem, there's nothing that indicates that they're like, well, we're testing to see if the school B has a higher average than school A. Or we're testing to see if school A has a higher average than school B. There is no indication of like we're testing it for a specific like being greater or being less than, which means it's a two-tailed test, which means we're not talking about being greater or less than, we're just talking about not being the same. That's it. The two-tailed test, not obviously, I don't like using that word, but maybe more understandably, would be that this is like the first test of like, okay, are the averages between these schools the same? And then if you're saying, hey, there's significant enough evidence to say that they are not the same, then you can do a test to say like, okay, well, is it greater or is it less than? And then you can follow through with that, would be a next logical step in this process. Okay, find the p-value. Notice here, we do not have matching data sets. That means that we only had so many averages. That's okay when we're doing a t-test. That's totally fine. So we don't need to have the same number of data in these guys right here. So if I go back into my calculator, I can just list all of my school A here and school B here. They don't need to match, and then I'll press my statistic calculations. So I would like for you to try this on your own. Hopefully you wrote down the instructions on the previous page. If not, I would recommend doing that now at some point in some place when you're practicing on your own. You should have like a set of instructions on what to do for this t-test. Okay, so I've entered in all my data. I went statistics, stat test, two sample t-test. My data input method is data, right? I'm just plugging in my raw data. So we say yes on that. We do A, B. Make sure that your alternative hypothesis is the correct alternative hypothesis. Make sure that you said yes on pooled, and then results in column C. Okay. Your p-value right here is 0.270 or 271. For 3 significant figures. And that's all we need to find, because then the next one says, okay, compare it to a 0.1 level of significance or a 10% significance level. We can see that 0.271 is greater than 0.1. And since our p-value is greater than the significance level, we do not have enough information to reject the null hypothesis. We conclude that the averages are the same. Maybe we can say the averages between the two schools. Is the same. Ta-da! Okay. Last problem. In 1936, R.A. Fisher published a paper investigating similarities and differences in the measurements of flowers of 50 plants of the 3 species of those 3 iris species. The following table shows the summary of the measurements of petal length of 2 species. Assume that the petal length of the flowers follows a normal distribution. Hey, cool. The variance is the same. Hey, cool. Those are the 2 criterions in order for us to be able to calculate a t-test statistic. Again, you won't be asked, I don't think, on an IB exam to determine whether or not you should follow through with the t-test, but it's something good to know, just in case it does pop up at any point. The size of the iris versicolor flower seems to be bigger than the iris virginica flower. Based on the information about petal length, test this observation at a 0.01 level of significance. So notice here that we're given a summary of data. We're not given a bunch of raw data of actual length. They took all of the raw data, because it was a lot of raw data, and they said, okay, we're going to summarize the data. Here's the mean, here's the standard deviation. And we can still do our t-test calculations with that information. So first, always first, let's state our alternative and our null hypothesis. Go ahead and tell me what our null hypothesis is. As always, the null hypothesis is that it should remain the same. And we can see here that the averages are different. And what we're really testing here is there a significant difference based off of the word significance level, right? So is there a significant difference here between the averages to determine that the difference between them is not by chance, that it's actually happening because of what this type of flower is. And so that's what we're saying here is, yes, we can see that the averages are different, but we're trying to determine whether it's significantly different enough to determine that it didn't happen by chance. Okay, I want you to go ahead and tell me what the alternative hypothesis is. Since it says in the words here, it says the size of the versicolor flowers seems to be bigger than the virginica flowers. So the versicolor ones, that's U sub 1, they say, well, if anything, it's definitely that this average is greater than this average. And so they've mentioned that in the words here. And so then that gives us enough information to tell us, oh, this is the type of test they're trying to run. So here are our null and alternative hypotheses. We are then going to go to our calculator, delete out all the other stuff, and we actually don't have to input any data into a stats list. You can do this calculation in your stats list, or you could do it in your calculator. So I'll show you what it looks like in your calculator. You could do the exact same thing here in your stats. But if I go back to the calculator guide, to the scratch pad. I'm going to go to menu. I'm still going to statistics, which just happens to be 6 now. I'm still going to stats test, which just now happens to be 7. And we're still doing a 2 sample t-test, which stayed as 4. Here, your input method. We are not inputting data. If you scroll over, you've also got an option for stats. You're putting in the stats. Okay. X bar is your average. It's the average of your first guy, and that's 55.52. X1 is your standard deviation, and your standard deviation is 5.52 with that data. N1 is the number of trials that you did, or the number of things that you looked at. And it told us that we looked at 50 flowers. I'm assuming, because how the textbook ran this calculation, and I know that this is what the numbers we need to put into our calculator are to get the numbers that the textbook gave me, that they mean 50 plants of each of the 3 species. But that's something that confused me when I was going through this problem, and so I would understand if it confuses you. But I am assuming, because of how I know the numbers are supposed to work out, that that means 50 for those guys, that we tested 50 of the versicolor flower, and these were the results. We then do the same thing, but now for the virginica. 50 again. So again, this is that thought of like, was it 50 total or 50 each? How much of each? I'm assuming they meant 50 each. Okay, Alternative hypothesis is that your average is greater. So I will scroll over, pick the greater version, go down, pooled yes, always, and then hit OK. And then this is what your test results look like when it's not in a table in your statistics thing. I think we saw it in our chi-squared, but your p-value is still there. If you did it in your stats list, you might have just seen 9.21. If you scroll down and highlight over it, you'll see that E negative 20. That means that we're talking about 9.21 times 10 to the negative 20th power, right? That E means a scientific notation. That means that we're moving this decimal 20 times to the left to make it an incredibly small number, which means really what your calculator is trying to tell you is that this is zero. It's zero. So when we're comparing it to a significance level of 1% or 0.01, 0 is less than 0.01. So since our p-value is less than our significance level, we have enough information to reject the null hypothesis. We conclude that the average petal length is longer for the iris versicolor. Ta-da! All right. Those are our t-tests. We saw 3 different situations of a t-test. We saw like a really, really basic one of just a straightforward as kind of like your introduction to the t-test. We then had one that was pretty much the same, but just showing you like, hey, you don't have to have the same amount of data in order to compare your data. And then for 3, we saw how we can use a summary of data to be able to still calculate the t-test and what that means in all of our calculators. So these are all of your tests, and we are going to spend the rest of this unit just practicing it and practicing it and practicing it and having them all mixed in together and knowing when to choose which one and all of that. So that's what we're going to spend the rest of this unit on. We're going to spend a significant amount of time doing that. Good job today.